Lesson 6. Capacitance. Section 6.2. Dielectrics. This is a simple atomic model. It consists of a negative charge bound to a positive point charge at its center. In the presence of an electric field, the orbit of negative charge is distorted. This displacement can be represented by another model, where positive and negative charges of q coulombs are the net charges on the edges. A vector p is defined as qd, where d is a vector from the negative charge to the positive charge. P is called the electric dipole moment. The unit is coulomb meter. Polarization P is defined by this equation, where dV is a differential volume, and n is the number of dipole moments in the volume. It is the dipole moments per unit volume. The unit is coulomb per square meter. This type of polarization is called the electronic polarization. This effect occurs in all atoms under the application of an electric field. This polarization effect is small compared to that of orientation polarization. Then let's look at orientation polarization. Some dielectrics, like barium titanate, have permanent molecular dipoles. In the absence of an electric field, the directions of these dipoles are random. When an electric field is applied, the dipoles rotate in the direction of the field, creating a very large polarization. The relative permittivity of barium titanate is more than 1000. Let's learn how the orientation polarization contributes to capacitance. This is a cross-sectional view of parallel metallic plates. Between the plates, there is air. The relative permittivity of air is almost 1. If a voltage V0 is applied to the plates, then positive and negative charges are induced on the facing surfaces. The surface charge density ρ is given by this equation, where A is the surface area. The electric field intensity E0, which is expressed by this equation, is generated. The unit vector AL is directed as shown in this figure. E0 denotes this electric field intensity without a dielectric material. The voltage source is removed. The surface charge will remain on the surface unchanged. Then a dielectric plate is inserted between the metallic plates. In the dielectric material, electric dipoles will align along the electric field. The density of aligned dipoles is proportional to the intensity of the electric field. The charges of facing dipoles are cancelled. The charges on the surface of the dielectric remain uncancelled by the dipole charges. The charge on the dielectric surface cancels the charge on the conductor surface. After the cancellation, the number of electric field lines is reduced compared to the case without the dielectric material. The electric field intensity E, which is weakened by the dielectric, is given by this equation. Epsilon R is the relative permittivity of the dielectric material. Epsilon R is defined as the ratio of E0 to E. According to section 6.1, the voltage V across the dielectric is equal to ED, and it is epsilon R times lower than the voltage V0. Thus, the capacitance C with the dielectric is epsilon R times larger than the capacitance C0, which has only air in the gap. Exercise 6.2.1. Pause the video, and answer the problem. The difference from section 6.2 is that the voltage source V0 is not removed, when the dielectric material is inserted between the conductors. The answer to exercise 6.2.1. Pause the video, and check the answer. Exercise 6.2.2. This is your homework. Pause the video, and answer the problem. The difference from section 6.2 is that the thickness of the dielectric is reduced by half. Exercise 6.2.3. This is your homework. Pause the video and answer the problem. The difference from section 6.2 is that the area of dielectric is reduced by half. The author of this material is Takeshi Furuhashi, Professor Emeritus, Nagoya University. If you have any questions, send emails to this address.